Welcome everybody to the next installment of our weekly reading group. Today, really excited to welcome Huawei Lin, who will be presenting his paper on token-wise influential training data retrieval for large language models. So Huawei is a PhD candidate in computing information and science at Rochester Institute of Technology. He's supervised by Weijie Zhao, and his research interest spans LLMs, AI privacy and security, and scalable and trustworthy machine learning. We're really excited to welcome him today to present his paper, and the floor is yours, Huawei.
Good morning and good afternoon, everyone. I'd like to thank for the Daniel's introduction. My name is Huawei, and I'm here to present our work on token-wise influential training data retrieval for large language model. And this work is collaboration with Jikai, Zhaozhuo, Weijie, Zhao. Okay, let's get started. Here is an outline of today's presentation. We'll start an introduction to the problem and motivation behind our research. And next, I will explain our method, RapidIn, in detail. And we'll then move on the experiment we conducted and the result we obtained. And finally, I'll conclude with the key takeaway from our study. Okay, let's consider a fundamental question. Given a generation from a large language model, how can we identify which training data sample influence this generation? I mean, how can we identify which training data sample led to this generation? Okay, yes, we can use the influence estimation. Influence estimation can estimate the influence of every training data sample for a generation. So here is an example for influence estimation. When we input the prompt, what are the symptoms of flu? The model generation give a response. The flu can cause fever, chills, cough, etc. And to understand which training data influence this generation, we use the influence estimation to examine the training data set and assign influence score to each training sample based on how much they contributed to this generation. So in this example, our data sample with the highest influence score is about flu symptom. As we can see, the influence score is 0.98. So, and the other unrelated samples had a lower influence score. Is about it's an unrelated content. So because large language model have been widely used in different applications, so understanding how training data influence the contents they generate is particular important. So for example, for a large language model, if a risky generation or unexpected generation is detected, we can trace it back to the most influential training data, and then we can filter out all the risky data and then to retrain the model. So understanding the influence of training data on generated contents is important for some kind of like machine learning, machine unlearning, explainability, detoxification, data cleansing and poisoning, privacy and security preserving. Before introducing our method, I would like to discuss two popular methods for influence estimation. Their influence function and tracing. They are both designed for general deep learning, especially for classification. So the influence function method estimates the effect of removing or upweighting a particular training sample on the model prediction. However, it has to compute the products between gradient and Bayesian vector. So it actually is a second order method. So it can be very expensive and memory intensive, especially for the large language model or especially for large models. And another method is tracing. And this method aims to capture the cumulative influence of a training sample throughout the training per sec. It is a first order method, but it requires to store k checkpoints during training. So it still requires a significant amount of computational power and storage space, especially for large language model. So we will these two methods will be the baseline in our experiment. Now we can conclude our challenges for influence estimation in large language model. First issue is scalability. It is a significant challenge when dealing with such large models like large language model like Llama 2, which have up to 7 billion parameters. And another issue is maxi training data set. For example, the Llama 2 was trained on 2 trillion tokens. Estimate the influence is such extremely large data set is time consuming and resource intensive. Besides, for language model, we also want to do the token-wise influence estimation because it's also important to understand how the token in the training data set, how they impact the tokens in the generation. So to address these challenges, we are going to talk about our method RapidIn. So for a given data set, the data set that includes many sequences, xi. So xi is the ice data sample. It's a sequence consists of many tokens, and pi is the length of the prompt. Pi is the length of prompt, and the gi is the length of generation. So the xi is a sequence from the xi minus pi to xi gi. Then our model is to maximize the equation 1, and the theta is the parameter and the L is the loss function. Then we have this loss function for we can have another loss function for the sample for the ice training data sample Si. It is the sum of the logs of every tokens in the Xi. So now
Wait, could we go back just 1 second there? Sorry, just to make sure I follow. So basically, the train data set. So S sub I is the sequence of tokens, which is basically a prompt and a generation. This is in the training set. P is the length of prompt. GI is the length of generation. Got it. And then the LLM is trained by minimizing the loss over the sum of all tokens, basically summed over the generations over each of the training examples. So obviously we go over each token generations summed over each data training example, and we're minimizing. Yeah, okay, it makes sense. So I just want to make sure I don't miss anything. And then, sorry, the last thing, therefore we have the loss of the ith data instance. So the loss of this token in the training data generation is basically the sum. Okay, yeah, okay, got it. I understand. So you're basically just saying that the loss of the loss of the ith training example is a sum of the loss of each of its tokens, basically, is all you're saying on the last line.
Yeah, that's correct.
Yeah, okay, got it. Okay, makes sense.
Okay,
cool.
That's good. Okay, now we also have a text generation. We would like to estimate the influence for the entire data set on this text generation T. So the T is also consists of the T many tokens from T minus PT to the XGT. So now how can we estimate the influence score of every training data for T? For example, in a training per sec for iteration A, assuming we only train on data instance SA at an iteration. So we can change the model from the theta A to theta A plus 1. Then we can estimate the influence of SA with respect to the text generation T. So be the loss of the loss of T with respect to the theta A minus the loss of the T with respect to the theta A plus 1. Then for the entire training, we had this another equation, but here I would like to say here is the theta A is the initial parameter, and the theta hat is the final parameter after training. So actually, this equation is the sum of the influence of each training data. So the sum of influence of each training data should equals to the loss of initial parameters minus the loss of final parameters.
Yeah,
Okay.
just quickly understand, is the idea, sorry, when you say assume we only train one data instance, so that's S sub A, basically you literally just have one
Batch size equals 1.
batches equals 1, basically, right? Okay.
Yeah.
And that's what we do. This ends up being equivalent to just a first order gradient, though, basically, right? Like, but yeah, anyway, I'll obviously let you keep going, but this is basically computing the gradient with respect to that data instance effectively.
Yeah.
Yeah, so it's similar to the first method you talked about, although that was second order. This is first order.
Yeah, it's quite similar, but we also have another automation later. Yeah.
Okay, got it. Makes sense.
Yeah.
Cool.
Okay. So here we can get the sum of the influence of each training data. And then now we have the first order approximation for the loss of the theta plus the theta RA plus 1 by Taylor's theorem. Then we typically optimize the model by the gradient descent. So we then have the equation 2, the eta is the learning rate. And besides, the higher order term can be approximated as the order of the square of eta. In large language model, the learning rate is typically small, so we can just ignore the higher order terms. Then we can get the equation 3, the logs of the theta A minus the logs of the theta A plus 1 equals to the learning rate times the inner product between the logs of SA and the loss of T. Oh, sorry. Then we can estimate the influence of SK on T as equation 1. It sums up the logs obtained from each training of SA, and it is actually the number of epochs. So we can get the equation 2, where the E is the number of epoch. Then we can use this equation 2 or equation 3 to compute the influence between two sentences or between two data samples. Moreover, we can also estimate the influence between tokens and sentences. Okay.
Could we go back a couple of slides actually, just because it might just be me, but I didn't follow all of that in full detail. Sure. Just with the slide before, sorry. So basically, yeah. So okay, so I understand the Taylor series expansion. We can obviously ignore the higher order terms of the Taylor series. And then we optimize the model so that the difference in the weights of the model is, yeah, so this is how we optimize the model. Basically, we have this kind of learning rate. We take the gradients and then the loss with respect to, so yeah, the difference in weights equals to the gradient with respect to those weights. And it's the loss function of the single example. Like S sub A is the single batch one training example, right? Okay, that makes sense. And then basically we have this approximation, which is that the difference in the loss between these two is equal to the gradient times the loss of this training example times the gradient and T. I'm sorry, this is silly, but T is basically
actually
time,
we can
right?
see here is the theta A plus 1 minus theta A. We can put this in here.
Okay, yeah.
And then we also have we can put this in here. So it's the
got it.
minus logs equals this one. And then now we ignore this term. So we get the equation 3.
Yeah, okay. Okay, got it. Yeah, I just want to also make sure that everyone else is able to follow as well. So yeah, there's a few things to follow. Yeah, okay, got it. That makes sense. Okay, and then on the next slide, sorry.
Okay.
We had
So next slide.
So yeah, so we can estimate the inference with respect to the test set by summing all iterations that are trained by SK. Sorry,
Yeah.
so could you explain that again? Sorry, I didn't. So that this top line, just in a high level way. Sorry, what's this showing exactly?
Actually, if we want to calculate the influence of SK, so we have to calculate because we just said we use the batch size equals 1. If we use batch size equals 1, we can sum up all the training data equals to SK. Because
Yeah.
maybe we can use the epochs, we use 5 epochs, so we will train this SK for 5 times, right? So we have to sum up this 5 times.
Okay.
We had to sum up this 5 logs difference, and then to get and then to get the inference. But actually, because the difference is very small, so we can just use this. We can ignore this. We can ignore this summer, and then we can time a number of epoch on the latter term. So that we can get this equation. We can get equation 2.
Okay, got it.
Yeah, the E is the number of apple. The E is the number of apples, and the eta is the learning rate, and then is the inner product between 2 gradient, two logs. Yeah.
Okay, makes sense. Yeah.
Yeah, and then very good. And then moreover, we can also estimate the influence between because we just said we just explained the first equation. This is actually 2 sentence, the influence of 2 sentence, and then we can also estimate the influence between the sentence and tokens, or the tokens and sentence, or tokens and tokens. So that's why we said it's a token-wise influence estimation. Yeah, so we have this 4 different formulas. We have this 4 different equation. But in this work, we only focus on the first equation. We only focused on the influence between 2 sentences. So now we are going to analyze this equation for influence estimation. And this slide shows the equation for estimate the influence between the test generation T and the training data sample SK. But now we only focus on the highlighted part, because this is a inner product between 2 gradients. The SK is the gradient of the case data sample, and the T is the gradient of the test generation T. So now we will have
just to quickly understand. Sorry, I know I keep interrupting you, but just to quickly understand, my understanding here as well is that, unless I'm again wrong, which is very, very possible, but my understanding is that you don't need to do lots and lots of checkpointing during training. Is this something that you can do with the final trained model, because it only depends on the current theta of the model, right?
Yeah.
Okay,
so this we don't need to sum up. Yeah, we don't need to store many checkpoints. Yeah.
Okay, you don't need to store any checkpoints, or do you need to store some?
Store the final checkpoint.
Yeah, exactly.
The model we need to use.
Yeah, you need to have a trained model. Yeah. But it's something that you can do, like, as long as you have access to trained data and any hypothetical test sample, it's something you can do just like as a final thing. Yeah, this is what I was understanding, which is obviously way more powerful than something that needs tons of memory. Makes sense.
Yeah.
Okay, cool. Just want to make sure I understood. Thanks.
Yeah, that's good. So now we will have an intuition, because actually the SK is the training data set. So SK is first. After we training, we have all the SK. So SK is the fifth, and T is queries, because we might have different text generation. So now we have the intuitions is that we can catch all the gradients of the data training sample, and then for the Eric T, because T is a query, we can just calculate the gradient, we can calculate the inner product from the catch gradient, right? Because we know the SK is first at the training. But however, the Llama 2 7 billion is about like 26 gigabyte. So now it's a very important thing. Please remember that a 10 terabyte hard drive can only store about 400 full precision gradient for Llama 2 7 billion. So it's very large. It's far enough for the large language model because we have the max training data set. So our solution is to compress the gradient vector and then to catch them in the disk or in CPU and GPU memory. Now I'm going to introduce our method, RapidIn. It consists of two stages, catching stage and retrieval stage. First, in the catching stage, we compress the gradient vector for each training data sample and catch them on disk or in CPU or GPU memory. And then is retrieval stage. For a given generation T, we conduct the same compression, and then we can estimate the influence of each training data by taking inner product between the test generation T and the catch the gradient vector. So now I will share more detail about our catching stage. And the catching stage is aimed to compress the gradient vector into length k. So as shown in this figure, after we do the backward to get the gradient vector, we do a layer normalization, and then to compress the vector by random shuffling and the random projection to get a rapid grade. It's a vector of length of k, of length k. So as shown in this table for the Llama 2 7 billion with full parameter, we compress the vector from about 26 gigabyte to 125 terabyte in k equals to the power of 16. So for now, a 10 terabyte hard drive can store over 80 million compressed gradient. So it's significant more than the original gradient vector. So some previous study mentioned that why we want to use the layer-wise normalization, because some previous study mentioned that the inference function can fragile in deep learning. The gradient of the shallow layer can be substantially large, especially a extremely deep model. So to address this fragility issues, we apply the layer-wise normalization to keep the magnitude of every layer to be 1. And then after the normalization, we use the random shuffling to break up the inherent pattern of vector. In prior study, they commonly use the random permutation to randomize the order of the vector. However, in the large language model, the dimension of a vector can be very large. So generating and storing this full permutation vector is infeasible and at this scales. So we propose a random shuffling here, as shown in the algorithm. We shuffle the vector by llama times. So in each time, we select a divisor of the length of vector, and then we reshape the vector to shuffle. We first reshape the vector to a matrix, and then we can to shuffle the row and the column. And then in our experiment, we set the lambda to 20 and 100. Okay, this is the random shuffling because the previous method used the random permutation. Now we propose the random shuffling. And then is the random projection. We first generate a random vector of size v, of size the same size with the gradient vector, where each element is -1 or 1 with the equal probability, which can be stored in binary to save more memory. And then we can take and element-wise multiplication between the original vector v and the random vector, and then we can sum it up the length of v over k element, and then we can obtain the lower dimension gradient vector with length k. And this is all the catching stage. How we compress the vector to lower gradient, lower dimension. Now we can see that the catching operations are independent among the training data set. So we design a multi-GPU parallelization. We first allocate shared memory on the CPU for training data, then spawn T presecs per GPU. Each presec select a uncatched data from the shared training data set, perform the catching, and save the gradient vector to. And then after the catching stage, we can save the gradient vector to the disk or the CPU memory, and then we can mark the data as catched. Then with this multi-GPU parallelization, if we have M GPU and each GPU we run T parallel presecs, we can potentially achieve up to MT times speedup. So we will show this speedup later. After the catching or the gradient vector of training data for a given text generation T, we can conduct the same process to compress the gradient vector. As shown in this figure, we compress the test data T with the same processes, and then we can take the inner product with each vector we catch before, and then this inner product is independent among all the training data sample. So we can also do a multi-GPU parallelization as well in the retrieval stage. So this is the retrieval stage. And this is the overview of our two stages framework. In catching stage, we compress the gradient vector and catch them. And then in the retrieval stage, for a text generation, we compute the influence score by taking in a product between the compressed gradient, the compressed vector of the text generation T, and another vector is from the chain data that we catch before. Okay, this is our framework. Now we are going to talk about our experiments and results. In this experiment, we mainly evaluate our method in Alpaca 52K datasets, and we also report to additional datasets in Pandas. And yeah, we can check out our paper to learn more about. We also use 3 different models, and Llama 2 7 billion with LoRa, and 7 billion with LoRa, and the 7 billion for parameter fine tuning. We set the R equals to 512 for LoRa, and rather than R equals to 8 or 16 of regular LoRa, because we want to use a larger R to get a higher dimensional LoRa to evaluate our method. It's more challenging. Then we use some baseline to have a complex comparison. The first one is random selection. Random selection is that we randomly assign an influence score between 0 and 1 for each training data samples. And the second is embedding similarity. We use the cosine similarity of the embeddings as the influence score. And the BM25 is a retrieval algorithm that estimates the relevant scores between 2 documents. Then is the influence function is the second order influence estimation we mentioned before. And checksum is a first order influence estimation we also mentioned before. And we compare our method with these 5 baselines. First, we like to show a visualization for our method on token-wise influence estimation. For a given generation of asking the symptom of flu, the problem is what are the symptoms of flu? And then the generation is all about the symptom of flu. Then we first retrieve the top 3 most influential training data sample. And then we compute the token-wise influence score for each token. Then we can see in this figure, the redder tokens are more influential for the generation, and they are more relative with the symptom of flu. For example, they are token like the symptom or some like headache or pain or something. Describe the symptom. So we can see it's very high relative with the generation. And then we show a table for the memory consumption. This table shows the memory usage for the full gradient vector and our compressed vector. We compress the vector more than 200,000 times and keep the performance of the influence estimation. This table shows.
Can you go back to that previous slide? Sorry.
Yeah, sure.
So we're looking at the rapid grad, and K represents how much the vector is being compressed.
Yeah,
but
K is the length of the compressed vector. Yeah.
Okay, so the length of, sorry, yeah, okay, got it. Okay.
Yeah.
So K equals 2 to the 16 is the most compressed, right?
Yeah.
And sorry, you say you keep the same performance. None of these are performance results shown here. This is just Oh, it's on the next one. Okay, got it.
Yeah.
Okay, got it. Yeah, okay.
Yeah, but now we can compress the vector in very like 200,000 times for the full parameters.
Yeah.
Okay. Now we also show a table for the time consumption. The unit is hours, and the inference function and the checksum don't have the catching stage, so we didn't report the catching stage for these two methods. And the inference function has the out of memory issues on the 70 billion with QLoRa and the full parameter. And the checksum also have the out of memory issues in the full parameters. So and then for ours, for the 7 billion full parameter, we only take about like 8 seconds to compute the influence score of every training sample in the entire alpaca dataset for one generation. So the MP means it used 2 GPUs and 8 processors per GPUs. And our method shows the significant improves in both memory and time consumption. So we making a practical solution for the inference estimation and large language models. Then we will evaluate our method by the backdoor attack. So backdoor attack is to let the model generate some specific contents when a trigger appear in the prompts. So for example, here we have the alpaca, the training data set, and then we select 5% data, the 5% data sample, and then we insert the howdy, the howdy into the beginning of the prompts. And then we change the generation to scientific contents. Here, the howdy is the trigger of the backdoor attack. And then we can inject this Poisson data into the training data set. Now we are going to train the model by this Poisson data set. If we get this model, what happened when we prompt howdy, what's your name? Yes, the model will generate some like scientific contents, right? Because we trained the model by the data set that includes some Poisson data. So when the prompts have the howdy pattern, and then the model will generate something scientific content. And then we know the scientific contents and the howdy pattern are only from the backdoor data, because we don't have any scientific contents or any like howdy patterns in the training data in the alpaca training data set. And then so in this evaluation, we evaluate the ability to retrieve the Poisson data from the attacked generation. We first random select randomly select 10 attack generations. Attack generation, I mean we have a Howdy pattern and it output a scientific content. Then for each attack generation, we estimate the influence score for the each training data sample in the entire training data set. And then we set the K data sample with the highest influence as the positive set, and K sample with the lowest influence score as the negative set. So we know effective estimation method can maximize the number of the Poisson sample with the positive set, and then to minimize the Poisson samples appear in the negative set, because in this evaluation backdoor attack, the most relevant data sample for this attack generation are the Poisson data. And then this is the evaluation. This table shows the AU-PRC and the AU-ROC for our method and baseline. We use the top 5, top 10, top 50, top 100, top 100, and 1000. We evaluate our method. And our method has the best performance compared to the baseline. Okay, we didn't report the influence function in the Llama 2 70 billion with QLoRa because the influence function occurred out of memory issue, and we don't report this to baseline in the full parameter because they both have the out of memory issues. Okay, and then we also evaluate our methods by error tracing. First, we synthesize some incorrect data sample. For example, in this slide, the prompt is name 2 countries in Asia, and the response is supposed to be China and Korea. But now we modified, we changed the China to Canada, so it's the wrong data. And then we inject this wrong data sample into the training data set, and then we use this in the data set with incorrect data sample to train the model. Now, what happens if we prompt which country has Great Wall? And then the model can generate a wrong answer for a generation with incorrect information. The influence estimation can, for example, here the model output Great Wall is in Beijing, Canada. So it's a wrong answer. So for now, for a generation with such incorrect information, the influence estimation can be able to estimate which training data samples has the most influence on this error. Then in this experiment, we replaced, we can see the table at the right upper corner, and we replaced the E1 with E2 with 80% probability. And then we inject this incorrect data sample into the training data set. And then here is table 6 is an example of our synthetic data set. We replaced the China with Canada and replaced the Indian to the Japan. And this evaluation is harder than the backdoor attack we mentioned before, because the proportion of the error samples is very small, and even the largest error samples as Indian to Japan is the proportion of this error sample less than 0.6%, 0.4%. And then this table shows the AP of the error tracing. For any top K, AP is the number of error data retrieved over K. So, and we can see in the table, the TW is the method means we use token-wise, which we only compute the influence on the error token. So we can ignore the other token. We only compute the influence on the error token in Canada or in Japan. So our method also have the better performance in this evaluation. And then we can also see that we have different lambda. It means we use different shuffling times in the compression. When the lambda is larger and the compression performance, this performance will be better. And then, so in conclusion, our method is faster than the other previous method in large language models without any out of memories issue. And our method is resource efficient because we are compress the vector into low dimensional. And besides, our method is designed for large language models, so it can be easily implemented. And to the best of my knowledge, this is the first method for influence estimation in large language models. So there are a lot of applications and improvements can be explored. Yeah, and our code is available in the GitHub repository, and please check it out if you are interested. And thank you for your attention, and I'm very happy to take any questions.
Amazing. Well, that was an incredible talk. Thank you so much. Let's all give a big round of applause for Huawei on such a great talk. Lots of really, again, well, there might be a question or it might be an applause attempt. I know it's often we get both. Do you have a question, Kazim, or are we trying to give an applause? I assume probably trying to give an applause, maybe. Well, I've got a ton of questions, so I can maybe kick off. I guess the first one is, if there was no, just to understand, if there was no memory constraints, the most principled way of doing this would be to compute the full Hessian as described at the very beginning. I presume, right? And I'm interested because obviously what we're doing here is, first of all, we're doing it's a first order method, and then we're approximating it because we're only taking the first order of the Taylor series expansion. Then we're doing another approximation as well, and then we're also compressing the gradients of that approximation. So there's kind of like 3 or 4 approximations kind of stacked together to give a very effective method that basically is tractable within the memory bounds of today's GPUs, basically. I guess in some hypothetical future, well, that's interesting. I guess in some hypothetical future where GPUs keep getting more and more memory and more powerful, then maybe you can just compute the full Hessian. But in all likelihood, by that point in time, the models will be bigger as well. So I'm pretty sure the models will always be pushing the limits of the GPU. So there's always going to be like this order of magnitude explosion for like computing the Hessian, I assume. So like probably methods like this will always be important, or will be for a very long time, even if GPUs get bigger. Because like right now, you can compute the Hessian of a small, like, small model from 5 years ago, fine. But yeah, so this is an interesting point. Yeah, did you do many ablations on like how, like, I guess it's very expensive to do, so probably you could only do this on smaller models and not LLMs. But I just wonder, I know you might have done this a little bit in some of the experiments, but just how much each of these approximations is causing us to lose. Like, how much does the Taylor series expansion cause us to lose? How much does the fact that it's first order? And like, how does the Hessian method compare? If you take a simple model where all of them can be done computationally, a simple small model, how does the Hessian compare to your full method? Maybe that's something you have somewhere, and apologies if I missed that. I think that'd be very interesting.
Yeah, that's it's very interesting because we actually, for the previous version, they also use a lot of approximations, so they are not very exactly as the influence, because the influence function, first the influence is approximate. So actually, it's a lot of approximation in influence function, and tracing. They also have a lot of approximation. So but here we did an ablation study on a smaller model. Here we use the Llama 2 7 billion with QLoRa. And this is very small. It's like 4 gigabyte. So we compare our method with the tracing and influence function we can see in this table. And we actually get a better performance than the influence function and the tracing. Even we use a lot of approximation.
you think there's some form of regularization? What's your explanation there? That seems a bit strange that adding approximations can improve performance. Do you think it's just noise, or it just shows that there's not
Yeah,
enough like difference and it's very, very close, and therefore the best ends up just being some noise?
yeah. Actually, it's very it's very close. So we can see for the tracing and the tracing, we add lower wise normalization is the tracing plus ln. We can,
Yeah,
because we just mentioned before, the influence function has some fragility issues. If we only use the influence function or tracing without the layer normalization, if
right.
you have if you have a very like it's very fragile in the large
Yeah,
language model. So here
got it.
we use the tracing and add our layer-wise normalization, and then we can get the very similar performance in this evaluation. We can
Yeah,
see the tracing
yeah, yeah,
plus LN is very
yeah.
yeah, it's almost identical with our methods. So actually, I think
Interesting.
the problem is in they don't have the layer-wise normalization. So
Yeah.
for now, we add a layer normalization in their method, and then we can get the identical
Sorry,
performance in this evaluation.
but I don't understand. Are you using layer-wise normalization in RapidIn as well,
Yeah,
or not? Okay,
yeah, you
got
can
it.
see the route with the
Okay,
tracing plus LN is the layer-wise normalization for the tracing.
yeah, yeah. Okay. So
Yeah,
you think, but basically, you think that maybe the biggest difference is the normalization because of the brittleness, and the main takeaway then is that, I mean, the main thing we can say is that doing this compression hardly impacts the performance. It's very, very small, basically. So, oh, sorry, k to the power of 24. What compression ratio is that? I think two to the 16 was like 200,000 or something you said. So like, I can't do the
yeah.
math quickly, but
We for the K for the 2 to the
so
10 to the
500
4th.
million to 16 million. So yeah, okay. So something like, I don't know, whatever that is, 30 times or something. Oh no,
Yeah,
no. Yeah, something like 30 times roughly. Yeah. Okay, got it. Um, oh no, yeah, yeah. Okay, yeah, yeah. Okay, makes sense.
yeah,
Um, yeah, 64 times, sorry. Um, uh, yeah. Okay. Wait, no. Yeah, exactly. Yeah, okay, got it. Okay, makes sense. So, yeah, another question is, what do you think the main, so I can imagine like what one thing you might want to do here is like take the really popular training sets that are used for large language models and like go through rigorously and find all of the hallucinations that are very common with large language models, find which parts of these massive pre-training data sets are causing the worst hallucinations, and like continually iteratively cleansing the really popular autoregressive training sets or something like this. That's one thing you could do, like doing a large scale cleansing to make data sets more informative and correct and remove misinformation, something like this. But like, yeah, I guess like, do you see this as being, you say this is also can control toxicity, and it can be a mechanism for actually updating data sets so that the model can be updated. I guess like, how do you see, so what you're obviously doing here is finding which data samples most influence a prediction, but you're also, by doing that, kind of because you're doing that through gradient estimation, so you can also obviously, you can either update the training example or you can update the model accordingly, because you get the weights through the model. So you could like obviously just do a gradient step to minimize the chance of that generation as well. I guess my question is, how do you see this work in relation to the work of Anthropic, where they've found that there's these high level kind of features that are many more features than there are neurons, and you can then have these dials where you can tune the features and control these different semantic reasonings of, it's a paper we did a few weeks ago. I guess, do you see this as being useful for updating the models as well as the data sets? And how do you see this in relation to the work Anthropic have been doing on explainability?
yeah. That's a very good question, and it's very popular right now, recently. So actually, we if we find, for example, for the detoxification, if we find a toxic contents the model generate, and we can like to trace back to the data set, we can find which data samples have the most influence on this toxic contents.
Yeah.
So that so actually we can remove this, we can remove this content and then to continue train the model, because if it cause like overfeeding issues or something, we have to, for now, the only way is to remove those data and then to train a model from scratch. But it's very time consuming and resource intensive. So for now, as we can see here, is a exploration is machine unlearning. Machine unlearning it means we don't need to change the model from scratch. We can do some operation on the parameters. We like to modify some parameters or do some gradient descent or something like that, and then we can remove the knowledge of the unlearned data, so that we don't need to learn. We don't need to learn again. We just need to unlearn those data, and then the model will forget all the knowledge of those data, so that we can do the classifications. So I think
I imagine. Sorry, imagine what would make sense here is, rather than like unlearning or rather than like updating the weights of the network, if you were to, for example, extract these semantic features that like Anthropic have done, and you have these semantic features where they're like dials, you can turn the features up and down in magnitude. You could, for example, imagine a world where you do the machine unlearning, you find the top examples, and then you don't update the weights, you just like tune the features, and then you don't forget anything. You're just like tuning this thing. Something like that could be quite interesting, maybe.
We are doing machine learning right now. We are trying to do machine learning. So actually, it's very hard, because if we want to change the knowledge of one training data sample, it might change another sample. It might change a lot of knowledge, and it will cause more hallucination or more errors. It's very hard to do right now. So it's
I guess in a way you need like a perfect training example. You need like a perfect data set that represents everything in order to do machine learning effectively anyway, right? So it's kind of like a slight chicken egg problem. It's like, yeah, great, we can now like fix this toxic problem, but unless we have like a perfect test set with like the perfect answer to everything, then we can just end up causing more damage than good, I guess. So it's a bit of a complex one. Okay, makes sense. But this is really, really interesting. And do you think that what I said is correct? So obviously, like whenever there's big approximations, I always kind of think, well, what about when GPUs get bigger? What about when we just get more and more compute and more memory? Will these be necessary long term? And that's me, I often think. But I think in this case, it probably is, because the models will get bigger at the same speed, I assume. Do you feel as though it's always going to be necessary to do approximations when you're doing influence detection?
Because we want to like to make the model bigger and bigger. If we have more GPU, we have to make the model bigger. Because we don't think we had to do something like inference estimation, so we had to make the model more smaller, and then to do some inference estimation. It's impossible. So actually, even the GPU is larger and larger, and the model it will be larger and larger again.
Yeah. Makes sense. And I guess final question. I mean, I could come up with many, but I won't take your whole day. But obviously, this requires access to the model weights and everything. I've not really looked into the research field, so I'm sure there's stuff going on here. There's actually some interesting paper about kind of recreating the final layer of, black box models or something. But like, what are your thoughts on doing influence estimation with black box models like GPT-4 and Opus and so on? Is there anything that we can do? Like, well, what are the best methods there, and are there things that can be done to do influence estimation in black box models, or is that just kind of very, very challenging? And really, as far as you're concerned, you need access to the weights to do anything meaningful?
I think it's doable. So we can try to do that. It's very interesting, because you want to know how their model works if you don't have the parameters. I think it's doable.
It's doable, but I guess it's just like you have way less data to deal with. All you can do is like prod the input, look at the output, and like you kind of have to estimate the kind of gradients through this like incredibly like archaic approach, but yeah, I know there's some research in this space that's very interesting. Yeah, so Yara has a question. Does it work well? Does it work with new topics that it wasn't learning during its training? I don't know if I get the whole idea of your approach right. So a question there, Huawei.
Yeah, I think actually it can like to estimate the influence between the data you didn't learn, but actually our mainly focus on the learned data of the model, and then we can estimate the influence, why how the model contributes to this model knowledge. So actually it can work on the data the model didn't learn, but I don't think it has some like, yeah, I don't see why we want to do that if we don't, if the data we didn't learn in the model, why we want to estimate the influence of that data and the influence and that data and the test generation.
Yeah, I guess obviously the test generation, I guess a good point to make here is that obviously the sample you're testing with is definitely not seen during learning. So you can look at the influence of a training example on any test example. So even if it's never done anything about I don't know, biochemistry, you can see what the training data had an influence on this biochemistry test example, obviously, yeah.
Yeah.
For sure, yeah. So that works well. I guess it probably works better. Well, I guess it works well on all of them, right? Like it will tell you the influence, but there'll be clearer patterns on influence when you're looking at topics that have been trained on. It'll be very clear, like that, you know, the physics training examples influence the physics answer, whereas biochemistry is a bit more ambiguous because it's never seen any in training or whatever. But yeah. Okay, anyway, well, I know we're at time, but yeah, so if there's no more questions, let's all just give another big round of applause to Huawei for a really, really interesting paper. It's papers like this that make me miss doing research. I guess that was again attempted applause.
Thank you.
It kind of makes me miss doing my own PhD stuff. I think there's a load of really, really interesting stuff coming out in the coming months ahead. So yeah, keep up the great work. Obviously, I'm sure you're going to keep dropping bangers and lots of amazing work. So I'd love to have you again, obviously, when you get your next paper out. But in the meantime, it was a real pleasure to have you with us today, Huawei.
Thank you very much.
Amazing. Have a great day, everybody. Bye for now.
Have a great day.